Okay, so 12.3 is probability. I mean, we've been talking about probability for the whole chapter, but so an experiment is any process that generates one or more observable outcomes. So like rolling a die, flipping a coin, those are all experiments. Sample space is the set of all possible outcomes. So it says, suppose you have the following experiments. List the sample space. All right, so flipping a coin. So flipping a coin has two different outcomes. What are the outcomes? Heads or tails, right? So your sample space, we usually write S equals, and we use those braces that you guys love drawing. And we do like heads, tails. You could write out heads and tails. I usually just do H and T. All right, rolling a die. So the different outcomes would be 1, 2, 3, 4, 5, and 6. Counting the number of stars in the sky. It's a weird one. So you could have 1, 2, 3, 4. Am I going to keep writing? No, dot, 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 right? So it's kind of a debate. Is there an infinite number of stars in the sky, or is it finite? I would think that it goes on forever, but maybe I'm crazy. So I'll do dot, dot, dot. Okay, so an event. Any outcome or set of outcomes in the sample space. So an event for each of those, like for part B, rolling a die, an event would be rolling a 2. You could have multiple sample spaces, like, you could have rolling 2 die, so you could have 1, 1, 1, 2, like we've talked about before. So an event in that case would be like rolling the number 3, like when you add the numbers together. So there's lots of different outcomes. So the set 2, 4, 6 is an event. That would be rolling a 2, 4, or 6, or rolling an even number. So you could have just one thing, or you could have multiple things in your sample space. All right, now probability of an event. The probability is always a number between 0 and 1. So a number between 0 and 1. It indicates how likely an event is to occur. So if I have 1 die and I'm rolling it, then the probability of me rolling a 7 is what? If I have 1 die. Is that possible? No, I only have 1 through 6. So that would be a probability of 0. Make sense? The probability of rolling a 1, 2, 3, 4, 5, or a 6 is 100%, right? So that would be 1 for your probability. Okay? So example 1, it says, suppose a box contains 50 candies, 20 are strawberry, 15 are grape, 10 are lemon, and 5 are orange. An experiment consists of drawing one candy from the box and looking to see what flavor it is. So what is the sample space of the experiment? So when I observe the flavor, it could be a strawberry, grape, lemon, or orange. You can write all of those out. I usually try to abbreviate them somehow. That's an O there. So then it says, what do you think the probability is for each color? Okay, so we usually write like the probability of, and then you write out strawberry, or you could abbreviate. So what's the probability of strawberry? Yeah, so it's 20 out of 50. So Kern says 40%, which is 0.4. So we usually write it as a decimal or as a fraction. So you could say or 2/5. Okay, then the probability of grape. Well, there's 15 grape out of those total of 50 candies. So 15 out of 50, I would divide by 5 on top and bottom. So 3/10, or 0.3. It's 30%. So we just go through each one. Probability of lemon is 10 out of 50. So 0.2, or 1/5. And then the probability of orange is 5 out of 50. So 1 out of 10, or 0.1. So then we say, well, what is the probability that a strawberry or an orange candy will be drawn? Okay, so probability of a strawberry or an orange candy, well, there were, let's see, 20 strawberry candies and 5 orange. So when I add them together and take it out of 50, I get 25 out of 50. So I get 1/2. So 50%. Okay. Sometimes it's really hard to figure out what the probability of a certain thing is, and it's easier to find its complement. So its complement is the set of all outcomes in the sample space that are not in a certain outcome. So it's like everything else. So the complement of A is represented by A bar. So see how there's like a little line above it? We call that bar. So A bar. You could also say A complement. Okay, so it says a single card is chosen from a standard deck of 52 playing cards. What is the probability that it is not a king? So if we have 52 cards, how many kings are in that deck? 4. Yeah, these are kind of hard. Sometimes I don't usually put card problems on the test because some people don't play cards. Some people don't know like how many aces or how many hearts there are. Okay, so there's 4 kings. So basically, if there's 4 kings, this means there are how many not kings? What'd you say, Kern? 48, right? You do 52 minus 4. Okay, so then the probability that you don't get a king would be, or let me write this out differently. You could write it out as probability of K with a bar on top of it, so K complement. So everything but the kings would be 48 out of 52. Which is 12 over 13. I usually leave my probabilities as fractions. You guys could write this as 0.923 as well. It doesn't come out nice and even though, so you've rounded that decimal. All right, you might also see complement like AC, like A complement, so A to the C. But usually you'll see a bar with the book that we have. Okay, number 2. So 2 dice are rolled. What's the probability that you get a sum greater than or equal to 4? Okay, this is kind of hard. Do you guys remember how we do anything when we have 2 dice? We have to think about that table, right? I don't want to draw that table out every single day. It takes a while to draw the table. Okay, so let's think about the complement. So we said greater than or equal to 4. So that means we'd have 4, 5, 6, all the way to 12. Okay, so what's the complement? So what's everything but those? Yeah, so something less than 4. So with dice, you could have 2 or 3. Those are the only numbers that are less than 4. You can't have 1 because you have 2 dice, so you have to have at least 2 dots, right? All right, so that means that we would have the 1-1 outcome, we'd have the 1-2 outcome, and we'd have the 2-1 outcome. That's it. So there's only 3 ways that you can get less than 4. And this is out of 36 total outcomes. So when we talk about the probability that our sum is greater than or equal to 4, it's everything else. So it's 33 ways out of 36. They're both divisible by 3, so you get 11 out of 12. It's an equal sign. Does that make sense? Okay. Another way to do these, if you have a complement, is you can actually find the probability of the other one. So notice how the probability for this one was 3 out of 36. Okay, that means that probability was 1/12. How's that related to the 11 over 12? So 1/12 and 11 over 12. Yeah, they add up to be the whole probability, like 100% of the outcomes. Right, they add up to be 1. So basically, if you want to find the probability that the sum is bigger than 4, you don't have to write this down. It's 1 minus the probability of the sum being less than 4. Right, it's 1 minus the complement. So it's 1 minus 1/12, which is 11 over 12. So that will help you out sometimes too. Okay, next up. Odds. Did you guys talk about odds in Algebra 1? Do you guys remember odds? No? Okay. So the odds that an event will occur can be expressed as a ratio of the number of ways it can succeed to the number of ways it can fail. Okay, this is very, very confusing because places like casinos use odds. They don't use probability. So when you're playing a game, you're like, oh, it says I have a 1 out of 3 chance of winning, right? It looks like this, 1 to 3. So you're like, oh, I'm going to win a third of the time. I'm going to try it. That's not actually what that means. If you see 1 to 3, that's not the probability. That's saying you have 1 way of winning, 3 ways of losing. How many total ways can you play the game? 4. So what's the real probability? 1/4. So see how that's tricky? You have even less than what you think you do. So it can be very misleading. Okay, so number 1, it says if the odds of winning a game in a casino is 3 to 4. Oh, we just kind of did this. So if the odds is 3 to 4, so that's 3 ways to win, 4 ways to lose. So when you see that, you're like, oh, 3 to 4, that's a pretty good chance. I have 75% chance of winning. No, you don't. You have a 3 out of 7 chance of winning, right? There's 7 total ways. So the probability is 3 out of 7. So that's not good. That's less than 50%. So why do they use odds instead of probability? It looks like you have better chances, right? Okay, so according to the U.S. National Center for Health Statistics, the chances of a male being born in 1990 living to at least 65 years of age are about 3 in 4. So notice how you said, well, we didn't say odds, did we? Let's say odds. That way I'm using that word so you can see it. Oh, no, wait. Maybe this is your probability. Yeah, because now it says the odds of a male living. So yeah, that is probability. So what are the odds of a male living to be at least 65? Okay, so if the probability is 3/4, probability is always kind of like your ways to win out of the total ways. This is kind of morbid. So the ways to lose would be the number of ways to die, right? So how many ways can you not win? 1, right? So there's 3 ways to win out of 4 total ways. So that means one of those ways had to be unsuccessful. One of those ways you would die. So your odds are 3 to 1. So basically you take that bottom number in your probability and subtract out top number. So what are the odds of a female living to at least 65? So your probability is 17 over 20. So there's 17 ways to be successful. How many ways to be unsuccessful? 3. Because you have 20 total, so they need to add up to be 20. Okay, so let's find the odds of each outcome if a computer randomly chooses a letter in the word Alabama. So let's talk about the probability of each letter first. So the probability of getting A. So how many A's are there? 4 out of how many total letters? Let me look. Yeah, 7. So 4 sevenths. Okay, so that means the odds of A would be 4 ways to get an A. How many ways to not get an A? 3. Make sense? So we just go through each one. So the probability of getting an L, well, there's only one L out of 7 total letters. So the odds of L would be 1 way to win, 6 ways to lose. And same with M. Oh wait, I guess B and M, right? So let's just say same as. Okay, so you could write out each one, but that's going to be the same as the B and the M, right? There's only 1 out of 7 of those letters. All right, independent events. So 2 events are independent if the occurrence or non-occurrence of one event has no effect on the probability of the other. Okay, so that's kind of important. So let's talk about things that are not independent. So things that are what we call dependent. Okay, if I put all of your names in a hat, and I'm like, okay, the first person I choose is going to get 5 extra credit points, and then the second person I choose is going to get 4 extra credit points. All right, I'm not putting their person's name back into the hat, right? So I pull out a name, and Matt is the winner. All right, I put his name to the side. And then I pull out another name, and Melvin is the winner. Okay? Now, here's how this works. You pulled out the first name, and there's, let's see, how many of you are here today? So 5, 6, 7, 8, 9, 10, 11, 12. There's 13 of you in here. So what's the probability that I pull Matt's name out of the hat to begin with? 13. So there's 1 name out of 13, right? 1 out of 13. But now that I've taken his name out, so he already won the first game, what's the probability that Melvin will win the next one? 12. 1 out of 12. There's 12 people left. Okay, that has changed your probability. Okay, that's what you would call dependent events. It depends on what happened in the first one. Okay, so independent has no effect on the next outcome. So even if you flip a coin 700 times, it does not matter what happened on the first 699 flips. So this is very strange for people because it's like if you had a coin that randomly landed on heads 699 times in a row, it still has no effect on the outcome. Your flip on that next one, on the 700th flip, is still either going to be heads or tails, and it's still a 1/2 probability for each one. Does that make sense? Yeah, that would be freakish, but it could happen. Oh no. All right, so if A and B are independent, then the probability of A and B occurring is going to be probability of A times probability of B. So this is not true for dependent events. Okay, so let's talk about these trees. So suppose you're flipping 2 coins. So this is my first coin. My outcome is going to be either heads or it's going to be tails. Then I'm going to flip it again. So these branches are going to represent the second coin. So after I get a heads, I could either get a heads again or I could get a tails. After I get a tails, I could either get a heads or a tails again. So this means our sample space is HHHT. So I just went along here and then along here. TH and TT. So if I asked you the probability of getting a tail on the second flip, there are 2 ways to get a tail on the second flip out of 4. So that's 1/2. Okay, it's 1/2 because it didn't matter what happened on that first flip. it's either going to be heads or tails in that second flip. So they were independent. Okay, let's try another one. So suppose you're rolling a dice and then flipping a coin. What's the probability that you get 6H? Okay, so you need to do each of your 1, 2, 3, 4, 5, 6 for the possibilities. And then each of those is going to have heads and tails. How many different outcomes do you have? 12 outcomes, right? Because you could have 1H, 1T, 2H, 2T, 3H, 3T. So you'd have 12 outcomes. So what's the probability that you get 6H? That means you'd go along here, and then you'd go along here. So there'd be one way out of those 12. So 1/12. So let's talk about what this is if we wrote it out. This would be the probability of getting a 6 and an H. I'll write it like that. These are independent events. It doesn't matter what I got on the first thing, on the dice roll. That's not affecting the heads or tails, right? The coin. So it ends up being the probability of 6 times the probability of H. Well, the probability that you get a 6 when you're rolling a die is 1 out of 6. The probability that you get an H is 1 out of 2. So when you multiply them together, you get 1 out of 12. When we construct these probability trees, what we're going to do is for the first branches, each of those probabilities is 1/6. So we'd write 1/6 on each of those branches. Okay, once we get to our 1 or to our 2 or to our 3, so once we get to the number, now the probability of getting a heads or a tail is 1/2. So you put 1/2 on each of them. And then we just multiply these numbers. So we say 1/6 times 1/2 gives me my 6H. I get 1/12. So it helps you quickly find the probabilities of each branch. Okay, the probability of losing a certain game is 0.7. If the game's played twice, what's the probability of losing both games? Okay, so we're going to play this game twice. We're either going to win or we're going to lose. And then we're going to win or we're going to lose. So I'm going to put the probability of each branch on here. So the probability of winning is what? 0.3, because the probability of losing was 0.7. So if this is 0.7, this is 0.3. They add up to be 1. That's 100% of the outcomes. All right, once I win, this doesn't affect the outcome of the next thing. My probability of winning again is 0.3. My probability of losing is 0.7. Probability of winning is 0.3. Probability of losing is 0.7. So the probability of losing both games means you would go this route. So lose, lose. So what do I need to do? Yeah, 0.7 times 0.7, so you get 0.49. So what's the probability of winning both games? 0.3 times 0.3, so 0.09. True answer. I like the note on your box. All right, so losing once and winning once. This one's harder. If you're going to lose once and win once, that means you could win and then lose, or you could lose and then win. So be careful with this one. So if you win and then lose, that means you'd have 0.3 times 0.7. If you lose and then win, you're going to have 0.7 times 0.3. Both of them give me 0.21. What do I do with those 2.21s? Yeah, you add them. So 0.21 plus 0.21 is 0.42. That's your answer. Okay, so let's try some examples with dependent events. So in a particular city, 13% of the population is age 65 or over. Of the people age 65 or over in the city, 42% are male. If you select a person at random from the city to answer a survey question, what is the probability that the person is a female that is 65 or over? Okay, this is tricky. So we want the probability that someone is female. Oops, I'm writing. It's not writing. So write female and 65 or over. Okay. Like this is an independent event. Okay, this one's definitely. Okay, I'm pretty sure this is a dependent event. Let me think about it. So 13%, 65 or over, under 65. So if 13% are 65 or over, that means 87% are under 65. Okay, once you select them, you have a certain, okay. So of the people age 65 or over in the city, 42% are male. So how many of them are female? 58%. Okay, we know nothing down here, but that's fine, because we're just asked to find the probability that a person is a female that is 65 or over. So that means you're going to go the 65 or over route and then female. Okay, this one is actually independent. Well, actually, no, it is dependent. I'm lying. This is dependent. I'll explain why. Okay, so we're going to do 0.13 times 0.58. So you get 0.0754. So between 7 and 8% of the people in that city are going to be female and 65 or over. Okay, the reason this is independent is because the probability of someone being female is not equal to 0.58 in the total population. Does that make sense? The probability that someone was female was we only had if they were female and 65 or over. We didn't say what's the probability that someone is female in this total city. Does that make sense? So it was telling you this depends on that branch that we already went on. So it's dependent. Therefore, okay, so remember that formula before? So if we did probability that you're female and 65 does not equal the probability that you're female times the probability that you're 65 or over. The probability that you're 65 or over is the 13 that we used. But the probability that you're female, we have no idea what that is. We only know the probability that you were female given that you were 65 or over. Okay, so it's kind of tricky, so draw a tree. All right, so Taylor has a basket of thread she used for craft projects. Didn't we just have Taylor in a problem the other day? Yeah, yeah, this is Taylor Rogers, Taylor Hines, right? Okay, the basket contains 6 spools of white, 4 spools of black, 3 spools of red, 2 spools of gray, 2 spools of yellow, and 1 spool of green. If she reaches into the basket and selects 3 spools of thread at random with no replacement, so she's not going to put it back, what's the probability that she will first select a red spool, then a white spool, then another white spool? It's going to be an interesting table. Okay, so let's start out the tree. So you have white, black, red, gray, yellow, and green. Okay, so for the white thread, you have 6 out of how many total? Has anybody counted them up? 18. For the black thread, you have 4 out of 18. The red, you have 3 out of 18, so just fill in the probabilities for each one. 2 out of 18, 2 out of 18, 1 out of 18. Okay, we're trying to find the probability that you do a red, a white, and then another white. So you're going to grab in 3 times. Can you guys tell this is going to be a messy tree? Yeah, so let's think about for the next one. Now when you're doing the branch, the white is going to use, you could have another white, a black, a red, a green, a yellow, oh, I guess that's gray, and a green. Each of those is going to have all 6 of those branches. Okay, we don't want to have to draw this. But what's happening to our probability? So once I've selected white, how many white do I have left? So we had 6 before, so now I'm going to have 5 left. Out of how many? 18 still? 17. It's changed. Your probability has now changed. Now the blue, we didn't select blue on the first one, so it would still be 4 out of 17 though. Can you see that? So I wrote 4 out of 17. The red, we haven't selected red, so we still have 3 spools of red out of 17, and so on. Okay, so that means our probability of doing red, white, white would be, well, probability of red for the first thing would be 3 out of 18. Once I select the red, how many whites do I have? I still have my original number of white threads, right? So I have, where were we? 3 spools of red still. Oh wait, we did 3 spools of red. I guess how many white do we have? So we still have 6 spools of white out of how many spools for the next one? 17. You've lost a spool of thread once you selected the first one. Does this make sense what I'm doing? Some of you look confused. All right, once you select the white, we had 6 spools of white originally. How many spools do I have now? I've already picked one of them. So I have 5 left out of a total of 16 spools of thread. That's how you would do that one. So each time the number on the bottom is changing because you have less thread. So I'm going to multiply my numerators. I get 90 on top, 18 times 17 times 16, 4896. And then I'm going to use my fraction button to reduce. So 90 out of 4,896 becomes 5 out of 272. That's your answer. You what? You're choosing white the second time, so its number changed. Yeah. Okay. I think we're going to run out of time. All right, we'll do expected value on Monday. Now your homework might have an expected value problem. Just leave that one blank, and then we'll finish it in class, okay?